Today we're going to be taking a look at Dynex's neuromorphic supercomputing engine and kind of, is it really as great as they say it is? And we're actually going to run some kind of real tests with this. And the way this is going to work is Dynex uses what's known as equations of motion, which is kind of, instead of dissecting section by section for compute, it's able to move itself across memory, and that's what makes it really efficient in what it does, and also kind of keeps it low power. And so we're not really talking about the blockchain side of it, we're actually talking about the real world compute that they're trying to build. A lot of people are calling this proof of useful work. And essentially what they've done is they've provided a bunch of files that you can use. You can actually run their solving engine on your system, and you can basically feed it some test files, and it'll basically run through the calculations, give you the results, give you the timestamps. And one of the things that happens every year is there is a conference that is accompanied with a competition as well, and it's called SAT. And this year it's taking place in Italy. Last year, and SAT is basically theory and applications of satisfiability testing, and this is kind of identifying, the most efficient algorithms, and really the most efficient type of processing that can exist for compute. So this happens every year. There's a competition that goes along with it that is similar to like what a hackathon would be at a typical convention. And so last year, the winning participant, we actually have their program, and we're going to be running their calculations, which this is basically globally what they deem the fastest compute engine out there. And we're going to be comparing that to Dynex. We're going to be feeding the same input file to both systems and comparing the results to see if what they built, and which was deemed basically the fastest and the most efficient in the world at that time, is comparable to what Dynex is doing. And I'm going to be doing all of this on a Hive OS rig. So we're going to hop on over, and I'm going to do A2000s. First thing I'm going to do is, as you can see right now, I am mining dynex. I'm actually dual mining dynex Radiant and also mining Veriscoin on this rig. I'm going to stop the flight sheet so that we're not doing any mining at all. Alright, now we have no flight sheet, and I'm going to remote into the system. I'm just going to use Shell in a Box for this. Go ahead and get logged in, and we can see this system does have 10 A2000s. It also has a Ryzen 5950X in it. So bear that in mind as we're running through the tests. First thing we need to do is there's a library we need to install. So we're going to do apt install libboost-all-dev. And I already have this installed, but if you're running a fresh Hive instance, you may not have that installed. And then I'm going to create a directory. I'm just going to call this AI test. And this is just so I have everything in a folder. We're going to go ahead and move into that folder. And the first thing I'm going to do is I'm going to download the solver from the SAT competition. Again, this is from last year. And you can go to satcompetition.github.io to get this file. We're just going to do a wget to download that. And then we're going to unzip that file. And now we have a whole lot of files here. But what we want to do is there's several folders here. And this cassat_mab-hiwalk. This was actually the winning solver. So this is the one that we're going to work against. And first thing I'm going to do is I'm going to chmod this folder to make it writable. Go ahead and do that. And then we're going to move into that folder. Now if we do a list, we can see we have all of the code. It doesn't include pre-compiled binaries, so we need to go ahead and compile it. Just going to do a ./configure ampersand ampersand, and then a make command. Go ahead and run this. And this should not take long at all. It should just take a few moments. And it is done. And now, if we do an ls, we should have a build folder. So we're going to go ahead and move into this build folder. And in here, we can see we now have this cassette, which is basically the SAT solver that we're going to be able to feed a file to. Now we need to download some files. I'm going to clone the entire dynex solver repository. So to do that, we can just do a git clone for the dynex neuromorphic chip repository. Again, this isn't the miner, this is the actual, their virtual chips. And this is kind of how they simulate those chips. And then we're going to change into that directory that got made. It should be called dynex-neuromorphic-chip. And if we do an ls, we can see we've got some files here. Once again, we need to compile the dynex solver. So this one's a little bit different. And you're going to do GCC for this one to compile it. So you're going to, or sorry, G++. So you're going to do G++ dynex.cc, and then you're going to give it these parameters. Go ahead and hit enter. And this shouldn't take too long. You can ignore any warnings that you get. Now if we do an ls, now we have a dynex executable in here, but we also have this config folder. So if we do an ls on the cnf folder, these are all of the test files we can use. And these are all very similar, the only exception being the number of computes that each file has, essentially variables that we're trying to solve for. So this file has 100 variables, this one has 200, this one has 500, this one has 1,000, this one has 10,000, and this one has 100,000. Now the 10,000 variable is what they actually tried running during the competition, and they exceeded the 15-minute execution time. So keep that in mind. So what we're expecting, again, I have obviously a different system than what they did the testing with, but we're expecting cassette to take around 15 minutes to solve this because that's what was done at the competition. So to run those tests, we can simply do a /cassette, and then we can give it that input file. So for us, we're going to, I'm going to start with the 1,000 variables. There's no reason to run the small ones. Those won't take any time at all to run. So we're going to do the 1,000 file. If we go ahead and run this, here you can see how quickly that ran. And the total processing time was 0.22 seconds. Again, this is with the SAT solver. So now we can run the same thing with the dynex solver. And if we do ./dynex, and then for the input file, we have to do -i for input. And then we're going to point this to the same file, which is going to be the 1,000 variables. Go ahead and run that. And you can see that obviously that ran super quick as well. And if we scroll up, here you can see the time spent was actually 0.028 seconds. So significantly quicker, but small jobs. So, you know, it's hard to kind of tell with those. And you can see it did run with 8 threads, and it did verify the solution. Now if we want to step it up, we can run cassette again, but this time we can run it with the 10,000. And this is the one that took 15 minutes. So let's go ahead and run this and see how long it takes. It's been about 12 hours and it is still trying to find the solution. And I'm not going to let this finish running. We're just going to go ahead and terminate it. And then we're going to try the dynex one and let's see if it can solve it at, a decent rate. So we just do Control C, and here we can see it was actually 10.5 hour runtime. So now we're going to run dynex, and we're going to do 10,000, right? So that same file that we just ran for the past 10.5 hours. And let's go ahead and run this. Obviously that ran super fast, and one of the things you'll notice is if we scroll up, we actually can't see those initial outputs. So what we're going to do is we're just going to capture the time. And to do that, we're going to do, we'll do start equals $, parentheses, date. And then ampersand, ampersand. And then we'll do ampersand, ampersand, and we'll just do echo $start, ampersand, ampersand, echo date. What this should do is this should capture the start date, run it, and then output both the start date and the end date timestamps. And there we can see it took around a second. We're not going down to the millisecond level here. So, but obviously extremely fast. So we weren't even able to solve that thing in 10.5 hours with the basically last year's competitions, fastest algo, or fastest processor rather. And we were able to solve it in 1 second with the dynex solver. Just spectacular. And the last thing I want to do in this video is we're going to run the 100,000 test. See how long this one takes. This should take quite a bit longer, but it still shouldn't take too long if their solver is as efficient as they claim. And there we have it. It is solved, and it did it in less than a minute. In fact, around 48 seconds. So super fast on that. And this test wasn't indicative of, them actually necessarily using this for real-world calculations, but they were able to build basically this solver that is insanely fast with their equations of motion. And this is really cool to see, right? This could be adapted to hashing algorithms. This could be adapted across the board. That could be really innovative tech, and this is really awesome to see. I truly hope they are using this to actually do deep learning calculations, AI-based stuff. It would be really cool to actually see some real-world examples of them implementing this with the actual tests. Obviously, there's going to be, some concerns from end clients sharing that information. It's really cool to see that this is probably the fastest solver that I've ever seen. I do lots of calculations and lots of streamlining of code efficiencies at my day job, and this is probably the fastest solver I've ever seen in my life, and it's just evident by comparing it to last year's SAT results. And one final point that I did just want to mention regarding dynex and kind of what they were able to accomplish with these equations of motion is it almost seems like it could potentially lead to the detriment of proof of useful work. And what I mean by that is these calculations are so fast that it almost becomes a moot point that we would even need decentralized compute for this. I could easily see organizations just buying 1 or 2 systems and running the calculations themselves and saving all of that money. And so It's actually kind of a detriment to proof of useful work, especially for those lower end jobs. It would be advantageous, especially if they're repetitive jobs, for these companies to just buy the hardware, minimal hardware, and cycle it through this dynex solve algo. Honestly, at this point, that's kind of the only negative that I'm seeing. When the only negative that you're seeing is that it runs too fast, they've definitely built something that is worthwhile, useful, and could possibly be the future of compute.